Welcome to week 6 of Statistical Molecular Thermodynamics. In this first video of the week, I want to begin discussing entropy. So, turns out this nice studio I'm sitting in is about maybe 200 feet from the banks of the Mississippi River. And there's a bridge over the Mississippi not far from here. And I'd like you to imagine an experiment maybe many of you have seen. What if I were carrying a chunk of metallic potassium, standing in the middle of the bridge, and I tossed it into the Mississippi River, well below me, fortunately? Well, many of you probably have not actually seen it with potassium. You've seen it with sodium. Toss a chunk of sodium in water, it skitters around for a while, it makes hydrogen gas, the hydrogen gas ignites, there's a little explosion. It's all pretty dramatic. It's a lot more dramatic with potassium, it turns out. This is one of those don't try that at home experiments. But I guess what I want to emphasize is I toss that potassium, K, into the river, K plus H2O. There's a big explosion, and I make potassium hydroxide and a half a mole of hydrogen gas, assuming I don't ignite that hydrogen gas and end up making water with the oxygen in the atmosphere. Let me ask you to consider a different process. What if I take a flask full of potassium hydroxide in water, just like that little section of the river, and I bubble hydrogen gas through it? What happens? Not really much, right? The direction that it goes, we know which direction it goes, but why? Now, some might think, oh, well, it goes from potassium plus water to KOH plus 1/2 H2, because that's the exothermic direction. Heat is obviously released. Maybe it's exothermicity. Well, let me tell you about a process or two where there is no exothermicity, so the enthalpy change would be 0, and yet the process we would all agree from sort of common sense and observation is spontaneous. So let me take one example. Here I have two vessels separated by a stopcock, and at the moment that stopcock is closed. On the left side is an ideal gas, and on the right side is vacuum. That vessel is completely evacuated. I open the stopcock, and immediately, so this is a little bit of a thought experiment because in practice it would take a second, 2 seconds maybe, but imagine that I've got a big enough hole in my stopcock that immediately all the gas is equally distributed across both vessels. I'm going to do this in an insulated system. All right, so I build a lot of insulation around it. It's adiabatic. There's no heat transfer. So delta Q is equal to 0. But I expand it against a vacuum. The external pressure was also 0. And as a result, the change in internal energy, delta Q plus delta W, that's all 0. For an ideal gas, for which the internal energy only depends on temperature, since there has been no change in internal energy, there must also have been no change in temperature. This is isothermal. And given that, if I look at the enthalpy, which is delta U plus delta PV, given that it's an ideal gas, PV is just equal to nRT, but there's been no change in T, and there's been no change in U, and so the enthalpy change is 0. So the change in everything is 0. But I think we all agree that this only ever goes one way. The gas will leave the full vessel, and it will occupy the empty vessel until they both have equal amounts of gas, half as much as was in the original if I started with equal volumes. So why does it do that? Let's talk about another process. Let's imagine now that instead of having a full vessel of gas and a vessel of vacuum, I actually just have two different gases. I'll have bromine on the left, it'll be a nice, pretty brownish color, the bromine gas, and nitrogen on the right, clear and colorless. And again, I open the stopcock. I think we all suspect, feel certain, that given a certain amount of time, we would have two vessels, each looking equally about half as brown as the original vessel did, as the bromine and the nitrogen distribute themselves equally across the two vessels. Again, I'm going to do this in an insulated system, adiabatic, no change in heat. In this case, it's not that the external pressure is 0, it's that there's no change in volume. The volume available to these gases is always the same. So delta V is 0 for the overall system, and so the work done is 0. And hence, once again, delta U, which is the sum of heat and work, is 0. And same argument as before, these are ideal gases. If the internal energy doesn't change, the temperature doesn't change, and so the enthalpy doesn't change. And yet again, I'll mention, we're all pretty certain it only ever goes one way. You wouldn't start with a 50-50 mixture of gases and expect to come back a little later and just randomly all the bromines on one side and all the nitrogens on the other side. So what is going on? Well, evidently, the universe responds to driving forces beyond those associated with heat, work, internal energy. There also appears to be an influence of what you might call disorder. So there is a tendency to go to higher degrees of disorder or randomness in a system. And so you can find spontaneous processes, like the two I just outlined, that may be thermoneutral, so delta H equals 0. You can even see processes where it's endothermic. Delta H is actually greater than 0. Later in the course, we'll have a demonstration of at least one of those. But what they all have in common, if they're spontaneous, is that there is an increase in the disorder of the system. So we might offer a hypothesis, for instance, that systems spontaneously evolve to increase their disorder. And thus there's going to be an interplay between changing the energy of a system or increasing its disorder that both have to be considered when evaluating, is a process spontaneous? And so I want to explore this a little bit further, and I want to consider the heat transfer that's associated with a small reversible change in the temperature and volume of an ideal gas. Right? And so I'm going to rearrange the first law of thermodynamics to isolate the heat transfer on one side. It's reversible. It's du minus the reversible work. Remember, what is the change in internal energy for an ideal gas? It only depends on temperature. It's the heat capacity times dt. And for an ideal gas, for the reversible process, we know the pressure is nRT over V times dV. So this expression is how one might go about computing the reversible work. Now, it's actually this last term, nRT over V dV, that's slightly problematic. It's what makes delta Q a path function instead of a state function. And the issue is that you have a commingling of variables in that term. You've got a dV and a V, that's fine, that's the same variable, but you've also got temperature. So you have one term that's involving two different variables of the system, and it makes it an inexact differential, we would say. But let me attempt to ameliorate that situation. And in particular, let me divide both sides of that prior equation by T, the temperature. In which case, I eliminate the T that used to be in the last term. I get delta Q over T is equal to CV over T. CV may be a function of temperature, or we may be working over a region where it's a constant, but we'll just note that it can depend on temperature. But in any case, I have a term here that depends only on T and a term that depends only on V. So that means that the quantity on the left side is now not an inexact differential, it's an exact differential. It allows me to integrate on both sides. And so if I think about integrating this expression currently on the right-hand side, or more accurately, if I want to express this as something that makes it more obvious what the integral is, this is, the left side, the derivative of this integral, plus, these are just constants, nr, this integral, and of course there is a constant. If I take the derivative of a constant, it's 0, so we won't worry about the fact that that's thermodynamics. You're more often interested in changes than absolute values. The constant is arbitrary. So clearly then, del Q rev, reversible heat, change divided by temperature, is a state function because it's an exact differential. And we give it a name. We call it entropy. And we indicate it by S, capital S. So ds, the exact differential, that's why there's a D, is the reversible work. We tend to keep this reversible heat. We tend to keep this delta around just to remind ourselves that heat is not always a state function. It's a path function usually. But when divided by T, it makes this exact differential ds, entropy. And if you're wondering about the word, entropy itself comes from the original Greek, where entropia would mean internal transformation. So this concept, as we'll see, that relates to disorder, we'll see how entropy relates to disorder, it involves internal transformations. All right, well, that tells us how to construct this state function we call entropy. What we need to do next is explore its properties in a little bit more detail. And so that's where we'll be heading, entropy as a state function.